So today we're going to be going through the classic Dijkstra's algorithm. We're going to walk through the intuition for why the algorithm is the way it is, and also implement this in Python. So for Dijkstra's, we're always going to be given a weighted graph. It can be directed, it can also be undirected, and our task is to find basically the shortest path from the source to either one destination, or it could be to every single node. So for example, in this weighted undirected graph we have here, we could either say, find the shortest distance from the source, which is 0, to a specific destination, for example 4, or it could be from the source to every single node in the graph. And that is what we're going to be implementing today. So when you first look at a question like this, and if you've never done Dijkstra's before, your first thought is, hey, let's just do breadth first search, right? But I'll tell you why BFS doesn't work, right? So for example, you would look at this and say that, oh, you know what, like if you're trying to find the shortest path from 0 to 1, it's going to be this path. And if you're trying to find the shortest path from 0 to 2, it should be this path. But that's not correct, right? And that is because you see that from 0 to 2, if you take this path, your answer is going to be 8. But then if you actually go along this path, your answer is going to be 7, which is what you should return. And that is the distinction here. The distinction is that the graph here is actually weighted, right? The edges have weight. If this was a classic breadth first search algorithm where the edges did not have any weights, we wouldn't care. We would just do the BFS, right? And that's because BFS basically assumes that like all of the paths basically have equal cost. So for example, like in this case, BFS would assume that going from 0 to both the neighbors 1 and 2 would be equal. But in this case, because it's weighted, we know that it's not equal, right? Like this obviously has a cost or price of 4, and this obviously has so from 0 to 2, this obviously has a cost of 8. So how can we implement this? So we are going to be using a bit of breadth first search in the algorithm, but it's going to be modified. Now, the first thing that you need to sort of think about and problem solve is how are we going to traverse through this graph, and how are we going to keep track of the distances we have seen so far, right? So for example, when you are going from source to destination to, for example, 2, you see that it's 8, right? And then you're like, okay, great, but let me see if I can do better. And when you traverse along this path, you see that yes, you can actually do better, because you see that the result here is 7, which is obviously less than 8. So that would be how you update it as you go along, right? The distinction in Dijkstra's algorithm is something that's new, is that you have to use a min heap, okay? So we already know, we've learned all about heaps and priority queues probably in school, and we know that a min heap basically orders the heap in a way where you always have sort of the root, which is going to be less than all of the children. And when you pop from a minimum heap, you're always going to get the minimum value, basically, right? The node with the minimum value. And the reason why we're doing this is because in a breadth first search algorithm, when you just have a queue, you could just pop from it in order of whatever is first, right? So you pop at 0. But we can't actually do that. It's better for us to pop based on the lowest edge value, right? Because here we're trying to find the shortest distance. So we're trying to minimize the cost of our path. So we want to use a min heap so that every time you pop, you right away pop the sort of the lowest value, right? So that is kind of what we're trying to do. And so with this, right, like you kind of have to make sure that the first value you have in your heap is going to be the weight, and then you can store whatever node, right? Because if I just store the node here, so for example, like if I have 0 and then I pop it off, right, and then I put the neighbor, so I put 1 and 2, like that's not going to help me here because I need to know what the weights are as well, right? So we would basically store a tuple where we're going to store the weight first, and then we're going to store the node. Now you can say, why are we not storing the node first and then the weight? And that is because for a pop function, for a minimum heap, it basically orders it where it's going to look at the first value and pop based on that. So if you're using the node values, that's not going to help us, right? Because we need to pop based on the least weight. So that is kind of the intuition for, we can keep that. So that's kind of the intuition for using a heap. So now, how are we going to use this minimum heap to traverse through the graph and return the shortest path from the node to every single node in this graph? So the subtlety here is that we're obviously going to use breadth first search to traverse through our graph, but we need to keep track of the shortest distance we have seen so far, right? So just when we were going through this example, the first thing we did for the node 2 is that we said, hey, you know what, we've seen 8. And then when we take another path over here, we see that we have found something better, right? So that basically tells you that unlike a breadth first search algorithm where we have something like a visited set and we only visit one node only once, we can't really do that here, right? Because then you might not end up finding the shortest path ever, because you're only going to record the first path you see and that's it, you're going to return that. So you can't really do a visited set situation here. Instead, we're going to do something else. So let's build up the intuition for that, right? So obviously we can first push our source node, which is going to be 0, and like we said, that we can't just put the node value, right, because we have weights here we have to care about, so we're going to have to put the weight and the node. So for starters, we can just put 0, and then our source node happens to be 0 as well, which is fine. So after we do this, we can pop this value, right? So we can say, okay, so that's gone now. And then what are we going to do? We're going to push the neighbors into this heap, and we're obviously going to lead with the weights. So we can put the 4 and the 1, we can put the 8 and the 2. And so when we pop from this minimum heap, because it's a minimum heap, it's actually going to pop the lowest value ordered by the first element of the tuple, like we talked about before. So we're going to actually pop of the 1, right? And so we can keep a note of that, right? So we can always say that our node, for example, in this case is going to be 1 and our weight is going to be 4. So we can keep track of this. So now what do we see, right? When you're here, when you're at this 1, you notice that where else can you go? So now this is your node and your neighbors are the 4 here, you can go back to the 0, you can go to the 2. So if, for example, I did the same thing and I said, okay, great, just push 6 and 4, right? Just push this. That should be correct, right? Why is that no? Well, that's because if you just push the 6 here, then that's not really useful to us, right? Because remember, we're trying to return the shortest path from the source to the destination. So in this case, our destination is 4. So if you just return the 6, that's not really what we're looking for. We can't forget this part here, right? So that builds up the intuition that, hey, you know what, I actually need to calculate the sum of the path as I keep going along. So in this case, we know that the weight we have, which we have seen from the 1, is going to be 4, so we actually need to do 4 plus the 6. So how do you know that? That's basically going to be the weight plus the weight of the neighbor, right? So that's going to be 4 plus the 6, which is going to be the 10. So instead of appending the 6, we actually need to append 10 and 4, right? And the same thing here. So now there's something that you notice, which is that the 2 already exists in the heap, right? I have 2 has a value of 8 already in the heap. So this over here, this path here has a value of 7. So this 7 and 2, should I push this into the heap or should I not? What do you think? Well, this is where you need to make a check, right? Because we know that the 7 is better than the value of 8 we have here, we actually are going to push this into the heap. And we need to update this value, right? So this is why you see that you can't just do this and forget all this information, but you need to keep track of this somewhere. So one thing you can do is you can use something like a dictionary where you can map your node, your destination node, to the best distance you have seen so far. So for example, from 0 to 1, the best distance we have seen so far with what we have is 4. For 2, the best distance we had seen before this 7 was the 8. And then obviously after you go along this path and you notice that you can actually do better, you can do 7, we would just simply change this value and make it 7, right? So that is kind of what we're trying to do, and this is probably something new, but it's important. So you can't just, keep track of the edge values, but you need to build it up as you go, right? So for example, this path, when you would pop off the 2 and you go to the 3, you can't just push the value of 2, but you need to do 4 plus 3 plus 2, because that is literally what the sum of this path is, right? So this is kind of the intuition for this whole Dijkstra's algorithm. So it's very simple. Just to kind of recap, what we're basically doing is we're going to start off the minimum heap by having our source node. We're going to pop it off, we're going to push the neighbors, and every time we pop from this min heap, we're going to obviously, by the implementation of this method, we're going to pop off the minimum edge value, and then every time we're basically building up the sum as we go, and we check in our dictionary, we say, oh, is this better than what we had before? If it's better, then yeah, sure, update it. If it's not, we're not even going to bother pushing into the heap. So it's very simple, and then at the end you can basically return the distances or whatever variation the question asks for. So now that we have this all cleared up, let's go ahead and implement the code. Okay, so it's very simple. So we're going to have a minimum heap where we're going to obviously store 0 in the source node. And we're going to have some sort of a dictionary, a distance dictionary to map. So at the very beginning, we can map the source to 0, right? So just like breadth first search where we say while q, here we are doing while min heap, as simple as that. And obviously we're gonna have to pop from this min heap, right? So we're gonna say heap q dot heap pop, that's the first one, from this min heap, and I'm gonna record the weight and the node. And we're gonna go through the neighbors. So we're gonna say for neighbor in the adjacency list at the node. So I'm doing this because I'm given the adjacency list already in this question, right? If you're not, you know how to build it up. It's pretty simple. So in this case, my neighbor is basically going to be something like this. It's going to be like 1 and 4, where the first value would be my node and the second value would be my weight. Okay, so that's just kind of how it's provided. And so with this, obviously, you know that you're given this value. And so what do you want to do? So the first thing that might come to your head is that, oh, let's just push this, right? So we're going to implement that. So heap q dot heap push. So we're pushing into the minimum heap. And what are we exactly pushing? So remember, the first value of the tuple that you push has to be the weight, right? So we're going to do weight plus the neighbor at 1, right? Because the neighbor at 1 is going to be the weight in this case. So that's going to be the first value of my tuple, okay? And the second value is obviously is going to be the neighbor at 0, because that's the node. And so then you can say, okay, so now let's think about the dictionary, right? So a naive implementation is to do this after you push. So I'll show that here. So you might think like, okay, so let's just check, right? So if the neighbor at 0, which is my node, is not in this dictionary, right? Or if it's in the dictionary, or it's called distance, or if the distance at the neighbor at 0, so the node already exists, and the value that it stores is greater than the neighbor at 1 plus the weight, then you're going to say, oh, well, in that case, you should update it, right? So you should say that the dictionary at this node value, which is going to be the neighbor at 0, should actually be the neighbor at 1 plus the weight, right? Now, just think about this for a second, right? So remember when we talked about the situation or that example where you had the value of 8 for 2 and then you had the value of 7 for 2, right? So just think about this. If you're in a situation where you know, like the value that you have is, let's say, like a lot greater. So let's say 2 now has a value of 20. Should we even be pushing into the heap in that case? Not really, right? So this check is actually going to make sure that we don't keep pushing unnecessary things into the heap, right? Because then why would you even bother, right? Like pushing a value into the heap that already exists and probably is much worse than a path you've already traversed before, right? So that's kind of the reason why you should, before you push, you should do this check, right? And then obviously at the very end, you're gonna, so if you're doing a dictionary, you can just return the values, right? And so another thing that I'm gonna point out here is that you can actually implement this check even before you go through the neighbors, right? So that just like kind of reduces the number of steps your algorithm is going to take. So you can just say that, hey, you know what, if the weight that you have after popping is greater than the distance at the node, then like, is it even worth it for me to take all these steps and traverse through? Like, sure, you might catch that here, but it's actually better to do a check here and just make sure that you continue so that it skips this entire part. And yeah, so that's basically, you know, it's pretty simple. It's just a little bit new of an algorithm to think about, but that's basically it. And there's like multiple ways of implementing Dijkstra's, but this is just one way.